welcome to the deep dive. Ever feel like you're just, drowning in information sometimes, especially when you're trying to get your head around how these complex AI systems actually work? Yeah, you're definitely not alone there. We're here to give you that shortcut to being really well informed. And today we're pulling back the curtain on something pretty fascinating. We're diving deep into the core mechanisms, really, that let advanced AI systems handle those tricky multi-step tasks we throw at them. Our source today is a great lecture note by Jaewa Choi, who's an associate professor at George Washington University and also the PI for the CAFA initiative, that's FISCAPS. And Professor Choi introduces these three fundamental system parameters within a specific protocol. It's all part of something called the Impact CT framework.
Right. Impact. Iterative, multi-turn pipeline for AI collaboration technology. It's a mouthful, but the idea is powerful. Think about having a conversation, a real structured conversation, with an AI, where each turn isn't just random, but it builds precisely towards a goal. That's what we're unpacking. Yeah. Our mission here is to get into these three parameters, user turn, turn result, and system turn, and show how they orchestrate these really precise and crucially repeatable AI workflows. It's about understanding that internal logic, the gears turning inside, moving AI beyond just chatting.
Okay, let's unpack this then. These parameters, they sound less like vague ideas and more like the actual plumbing, the code that manages how information flows in these AI processes. How should we really think about them as concrete things?
Exactly. And what's fascinating and really key to the Impact-C framework is that they are concrete. They're actual variables. They store specific data at each turn of the interaction. The source material makes this super clear. It uses the hash symbol, hashtag for the turn number, starting at 1. So you'll see things like at TU1 at Taro or maybe at TR2 at Hare. It really emphasizes that these are distinct buckets of information.
Got it. So distinct buckets. Let's look inside each one. First up, at TU shag at nay. That's the user turn input. What exactly does that hold?
Yeah, at TU-shag at nest is pretty straightforward. It represents the user input at that specific turn. It's the main way you or maybe another automated system inject something new. It could be information, feedback, a command. It's the trigger or the core content for that turn's action. And critically, at TU1 at nest is always the very first input, so it kicks the whole thing off.
Okay, like the starting gun.
Exactly. So think of ATU1 at TUS. It might be you typing. I need a report on renewable energy advancements in Germany. Focus on solar and wind. That's your initial command. Sets the wheels turning. Then later, maybe turn 5 at TU5 at AT. It could be your feedback on a draft you just got back. Something like, okay, the energy wind part is good, but can you elaborate on the economic impact for small businesses?
I see. So it's direct guidance at different points.
Precisely. It lets you steer the AI's work in a targeted way.
Okay, that clarifies the user's role, but like you said, the AI has to respond, right? It produces something. So where does the AI's output, its result, fit in? Is that the at TR-shag at 2L?
That's exactly it. At TR-shag at TO is the AI's result, the output generated at the end of that specific turn. And it's not just like the raw chat history. It's the process product of the AI doing its job for that turn. Now, this parameter is absolutely critical for building what the source calls that chain of thought or, the multi-step pipeline. And here's the really key insight. The at TR-shag at TO from one turn, it's often used as direct, precise input for the very next turn.
Okay, so it passes the baton cleanly.
Right. It makes sure only the relevant, processed, often refined information gets carried forward. It stops the AI getting bogged down by, the whole messy conversation history. It's disciplined memory.
Kind of filtering out the noise.
Exactly. For example, at TR1 might be a collection of raw data, articles, maybe text extracted from a document after an initial gathering step. Then at TR2 could be something more structured, like a list of key policies and stats that the AI specifically pulled out and refined from at TR1 at T. It's starting to organize. And eventually at TRN out of TR10, that signifies the final polished result, maybe the finished report ready to go, with a concrete output for that stage.
Okay, so we've got at TU-shag, at for the user's direction, and at TR-shag, at for the AI's refined output from a step. But how does the AI know what specific tasks to perform at each step? What tells it, okay, use this input to produce that kind of output? That must be the system term prompt at TS-tag at a pin, right?
You nailed it. That's the crucial piece. At TS-tag at T, it stands for the complete system prompt, the task instruction sent to the large language model for processing at that specific turn. And this is where, the clever design or prompt engineering really happens. It's not the raw user input from TU-shag at LA, and it's not the AI's result from at TS-tag at AL. Instead, it's this carefully crafted set of instructions designed for the AI at that exact point in the workflow. Often, these at TS-tag edit prompts are built dynamically. They combine some base instructions with specific data carried over from previous turns, like that refined at TR-check at result we just talked about, or maybe the original user request from at TU1 at A. This is how you really guide the AI to do something very specific and useful.
Can you give an example of what that might look like?
Sure, imagine at TS2 at end. It might tell the AI something like, okay, look at the raw data provided in at TR1 at TR1. Your specific task now is to extract only the key policies, initiative names, and relevant statistics. Discard everything else? Very targeted. Or maybe later at TS5 at event, it could be. Right, based on the user feedback at TU5, in the draft report at TR4 at Canada, and revise the section on energy Wenda to include economic impacts.
Ah, I see. It's combining the user's latest direction with the AI's previous work.
Exactly. It provides these super clear, actionable directives. It's how you keep the AI focused and on track, preventing it from just, rambling or going off on tangents.
Yeah.
It's about control.
Okay, we've looked at TS-shag at and at TR-shag at N and at TS-shag at individually. The user input, the AI result, the system instruction, but the real power, I guess, is how they work together, right? How do they create that logical flow, that pipeline? Is there a standard cycle?
Yeah, absolutely. This is where the impact framework really shows its strength. These parameters work in a continuous logical cycle. It's the backbone of the multi-turn pipeline. So first, a user gives some input or feedback that gets captured as at TS-tag at TS. Straightforward. Then the system steps in. It formulates a precise task instruction, the at TS-tag at TS. And this TS is often pretty smart. It might incorporate the user's current input at TS-tag at TS, or maybe the result for the previous step at TF1 at TO1, or even both.
Okay, so it pulls in the necessary context.
Right. Then the AI gets this at TS-tag at task, processes it, and generates a new result at TR-shag at TIA. Now this new at TR-shag at result, it can go a couple of ways. It might be shown back to the user, asking for more feedback. If the user responds, that becomes at TSN+1 at TIA, closing that loop. Or it could be used directly as the main input for the very next automated system task at TSN+1 at TIA, just carrying the process forward internally.
So it can loop with the user or just chain along automatically?
Exactly.
Yeah.
Connecting this to the bigger picture, this whole structured systematic flow enabled by these parameters, this is what lets the Impact-D framework break down really complex problems. Huge tasks become manageable, sequential steps. And the result, you get more reliable, more precise, and frankly, more auditable outcomes from the AI. You can see how it got there. It's how AI can tackle a big project without just getting lost.
That explanation really helps clarify the mechanics, but let's make it even more concrete. The lecture note, you said, walks through a report generation example. Can we trace how these parameters work in that specific case, turn by turn?
Absolutely. Great idea. Let's say our overall goal is to generate a summary of maybe a dense research paper, and we want it for a non-technical audience.
Okay. Sounds like a common task. So, walk me through turn 1. How does it kick off?
Right. Turn 1 starts with the user. That's a TU1 at let. So you upload the PDF of the paper, and you type in your request. Summarize this paper for a non-technical audience. That's your at TU1 at let. The system then takes this and crafts a TS1 at light, the first system instruction. It might be something like, user uploaded a document, first task, extract all text content, make sure it's cleaned up for analysis.
Just get the raw material out.
Exactly. The AI processes a TS1 at light, and the result is a TR1 at let. This at TR1 at light now contains the entire raw text of the paper. It's stored, ready. It's our initial knowledge base for what follows.
Okay, makes sense. Raw text secured in at TR1 at late. What's turn 2? Do I need to do anything else as the user yet?
Nope, not necessarily in this turn. So no, at TO2 at late. This step can be automated based on what we've already done. The system generates at TS2 at late, it might say. Okay, AI, using the raw text provided in at TR1 at late, and remembering the user's original request from at TU1 at late, create a concise one-paragraph summary. Make it suitable for non-technical readers, focus on the core findings. See how it uses both previous pieces.
Yeah, it references both the text and my original goal. Clever.
Right. The AI processes this at TS2 at they, and outcome is at PR2 at day game draft summary. So at TR2 at they might contain something like, a recent study looked at how city parks can reduce stress. They measured cortisol in 100 people, found that 20 minutes in a park lowered stress markers significantly compared to just being in an urban setting.
That's a decent first pass, but okay, what if I read that draft at TR2 and think, it's missing something important? How does my feedback get incorporated? This seems like a critical loop.
Exactly, and this is where at TU3 at comes into play, enabling that vital feedback loop. The system shows you the draft summary at Tier 2 at AV, and you provide your feedback. Let's say you type, "This is good, but can you also mention the key limitation the study talked about?"
Yeah.
That input becomes your at TU3 at thing.
Okay, my specific instruction.
Now, the system crafts a very targeted at TS3 at rub. It might instruct the AI. Right. Your task is to revise the summary currently in at TR2 at rub. You must incorporate the user's feedback from at TO3 at app. To do this properly, you need to go back and reanalyze the full original text from at TR1 at HEPA to find the study's limitations. Then add that specific information to the end of the summary.
Wow. Okay, so it tells it exactly where to look at TR1 at and what to use at TU3 at to modify the previous draft at TR2 at.
Precisely. It's very directed. Finally, the AI processes at TS3 at and generates the final revised summary, which is at TR3 at VR. So TR3 at might now read, "Lowered stress markers significantly compared to an urban environment." However, the authors pointed out a key limitation was the small sample size, so the results might not apply to everyone.
That's much better.
And what's really fascinating here, if you step back, is how at TR1, at the full text, served as the knowledge base. At TR2, the first draft, was the object being worked on. And at TU3, at your feedback, gave the precise direction for that final refinement. It really shows the power of using these specific turn results as inputs for the next highly targeted task. It makes the whole process controllable and transparent.
That example really crystallizes it. So bringing it all together, what does this mean for, for our listeners, for the learner, the person trying to understand AI, maybe someone prepping for a meeting about using AI tools? We've just pulled back the curtain a bit on how these sophisticated AI systems aren't just guessing. They're actually managing information flow. They're breaking down huge, complex tasks into these smaller, manageable steps. It's not magic, is it? It's this, meticulously designed pipeline built on these three pillars. At TU Shagat Bear, at TR Shagat There, and at TS Shagat Attachag.
Exactly. It's engineering. And understanding these parameters, I think it gives you that aha moment. You see how AI can achieve precision and predictability.
Right.
It shifts AI from being this kind of mysterious black box to something more like a transparent, collaborative partner. You start to see the logic inside.
Yeah, you move from just observing it to actually understanding how it works.
Right. And if we think about the bigger picture, consider how understanding this framework could empower you, the listener. How could you maybe design more precise, more effective collaborative workflows? Maybe using AI, maybe not. Think about the complex multi-step processes you manage in your own work, your own field. Could breaking them down into these kinds of structured turns with clear inputs, tasks, and outputs, could that enhance clarity? Could it improve results, make things more manageable?
That's a really powerful thought to leave people with, thinking about applying this structured approach more broadly. Well, thank you for joining us on this deep dive into the nuts and bolts of AI collaboration. Really fascinating stuff. Keep exploring, everyone. Keep questioning. And we'll be back soon with another deep dive into the knowledge you need.